the deep dive. Today we're tackling something massive, the sheer size and cost of large language models. You've handed us a stack of sources digging into this challenge, and one paper in particular caught our eye. It's about a technique called BlockPruner.
That's right. LLMs are incredible, no doubt, but their scale makes getting them out into the real world, especially onto, less powerful hardware, a serious problem.
A bottleneck.
Exactly. That's why model compression is such a crucial area of research, and pruning, essentially cutting away the unnecessary bits, is a core approach there.
And your sources point out that while pruning exists, the current methods have limitations. Stuff like pruning entire layers might be, well, too blunt an instrument, maybe.
Yeah, it can be.
So our mission today is to deep dive into this BlockPruner paper and understand what makes its approach genuinely different, more maybe academically innovative, and how it aims to make these models smaller and cheaper without sacrificing their amazing abilities.
Exactly. We'll explore its core ideas, how it thinks about redundancy at a much finer level than maybe previous work, and the clever, sort of global way it decides what to remove to preserve performance. It's quite neat, academically speaking.
Okay, let's unpack this. At a high level, why are these giant LLMs such a hurdle right now? What's the core problem?
Well, the biggest issues are really computational demands and memory usage, especially during inference when the model is actually generating text.
Right, when it's doing its job.
Yeah, deploying them at scale or, on-edge devices becomes prohibitively expensive or sometimes just impossible because of these constraints.
Got it. And that leads us to model compression techniques. Things like making the numbers smaller. That's quantization, right?
Right, or having a small model learn from a big one, knowledge distillation.
Okay. But pruning, as you mentioned, is front and center in these sources. It feels like carefully trimming a complex plant, maybe. Is that a fair analogy?
That's a good way to think about it, actually. Pruning is about identifying and removing parts of the neural network that aren't essential.
Okay.
Traditionally, it's been categorized into unstructured pruning, which removes individual connections but often needs specialized hardware to run fast,
Ah, tricky.
and structured pruning, which removes larger, sort of easier to handle components like entire neurons or even layers.
Right. And the sources highlight that while structured methods that remove whole layers exist, like some of the baselines mentioned in the paper, I think,
Hmm.
they might be missing something. They talk about these methods overlooking finer grained redundancies within the layers themselves. What does that actually mean?
Well, earlier research had shown that some layers in an LLM might be less critical than others, and layer pruning methods worked by, removing or merging those layers.
Okay.
But the hypothesis BlockPruner starts with is a bit more nuanced. It's that even within those layers that seem important on the surface, there's likely still unnecessary complexity or fine-grained redundancy, as they call it, embedded deeper inside.
Ah, okay. Here's where it gets really interesting then, and where BlockPrinter seems to offer that academic contribution you mentioned. It targets these finer grained redundancies. How do they break down the complex LLM architecture to even look inside a layer like that?
So what they do is segment each transformer layer, which is the core building block of most modern LLMs, into its fundamental kind of minimal processing units.
Okay.
These are the multi-head attention block, the MHA block, and the multi-layer perceptron or MLP block.
MHA and MLP. Got it.
Yeah, and their paper argues, based on the mathematical structure of the transformer itself, that these can be formally treated as minimal residual blocks. They're like distinct units suitable for individual analysis and potential removal.
So they're not just eyeing whole layers anymore. They're looking inside the layer, treating these MHA and MLP pieces as the new smaller units for pruning. Did they have evidence for this idea before they started cutting things out?
They did, yeah. They performed some preliminary experiments using a local metric called block influence, or BI,
BI. Okay.
which basically gives a sense of how much a block's output changes when its input is slightly perturbed.
Right.
And the results shown in their analysis suggested lower BI scores at the block level compared to the layer level, which kind of supported their hypothesis that, yes, significant fine-grained redundancy likely exists within these MHA and MLP blocks.
Okay, so identifying these MHA and MLP blocks as the granular units is the first core academic innovation here. How does BlockPruner then decide which of these specific blocks to cut? Because I imagine picking the wrong ones could be pretty disastrous for model performance.
Absolutely, and this is the second major innovation, and it's quite different from previous approaches that often use those local metrics like the BI score or just input-output similarity. BlockPruner uses perplexity, PPL.
Perplexity. Okay, I've heard that term. It's a measure of how well a probability model predicts a sample, right? For language models, it's essentially how surprised the model is by the next word in a sequence.
That's exactly it. Lower perplexity means the model is more confident, more fluent, less surprised. It's a good measure of the model's overall predictive performance and fluency on some text.
Okay.
So they measure a block's importance not by looking locally at its inputs and outputs, but by temporarily masking it, essentially removing it for a moment, and seeing how much the model's overall perplexity increases on a small calibration dataset.
Ah, interesting.
A small increase in perplexity means the model didn't lose much fluency without that block. That suggests the block wasn't contributing significantly and is therefore a good candidate for removal.
That's clever. So they're using a global metric, perplexity, which reflects the model's ultimate task generating coherent text to gauge the importance of a small internal piece. It's like judging a single musician's importance in an orchestra by how much the overall harmony is affected when they stop playing for a second.
That's a perfect analogy, and it's an academically sound approach because it directly ties the pruning decision to the model's actual language modeling objective. They argue this is a better indicator of semantic fluency than just relying on local signal similarity, which some concurrent work was doing.
Okay, so targeting MHMO blocks for granularity, check. Using perplexity as the global importance metric, check. Those are two big academically driven ideas. What about the pruning process itself? How do they actually execute the cuts based on these perplexity scores? Is it just rank and cut?
No, and that's the third key innovation, the iterative search procedure. It's not a simple one-time ranking and removal.
Okay,
Instead, they repeatedly do this. First, calculate the importance that perplexity increase when masked for all the current blocks in the model.
right.
Second, remove the single block and the lowest importance score, the least critical one.
Okay, just one.
Just one. And third, they recalculate the importance scores for all remaining blocks on the now slightly smaller model, and they repeat this cycle until they've removed the target number of blocks.
Wow, okay. So they're not just making a list at the start and cutting. They're cutting one block, seeing how the model reacts, how the importance scores shift, and then deciding which block is the least important now. That sounds much more careful.
It is much more dynamic.
Like carefully trimming branches off a tree, like we said, checking how the whole tree looks and adjusting your plan each time rather than just deciding beforehand to lop off, say, the bottom third.
It's a very apt analogy, and the academic rigor here comes from understanding why this iterative part is necessary. Their experiments, especially the ablation studies detailed in the paper, clearly show that just using the initial perplexity scores to remove a batch of blocks all at once, it performs poorly.
Really?
Yeah, performance degrades significantly without that iterative search. It demonstrates that a block's importance, at least as measured by perplexity, is highly dynamic. It's influenced by the complex interactions between all the blocks, and those interactions change every time a block is removed. You really need that iterative feedback loop for the perplexity metric to work effectively.
That makes a lot of sense. So the method itself seems well grounded. Did they back this up with experiments?
Oh, yes. To validate these ideas, they conducted really expensive experiments. They tested BlockPruner on a whole range of popular LLMs, Llama 2, Baichuan 2, Qwen 1.5, and even newer ones like Mistral and LMA 3.
Okay, good range.
And they tested across the diversity of benchmarks designed to evaluate different capabilities, not just perplexity.
And what did those experiments reveal? Did this fine-grained, iterative, perplexity-based approach actually, pay off?
Absolutely. The results were quite compelling, honestly. BlockPruner consistently and pretty significantly outperformed the other structured pruning baselines they compared against, the ones mentioned in the paper.
How much better?
Across various models and benchmarks, it maintained performance much better, especially when they pushed for higher pruning ratios, meaning when they removed a larger percentage of the model's parameters or computational cost.
So it degrades more gracefully?
Exactly. It also achieved lower perplexity on standard datasets like Wikitext 2 compared to models pruned with other methods, even when the pruning itself was guided by a different calibration dataset like Alpaca.
Okay, so the evidence strongly supports their core academic hypothesis. Targeting those fine-grained blocks is indeed more effective than just pruning entire layers. It leads to better preservation of the model's capabilities.
Precisely. And they dug deeper into the redundancy of the MHA versus the MLP blocks themselves. What did they find there? Was one type more redundant?
That was fascinating, actually. Their analysis showed that, particularly at lower pruning ratios, removing MHA blocks, the attention blocks, resulted in less performance degradation compared to removing the MLP blocks,
Huh.
which suggests that maybe the MHA modules initially hold more redundant capacity or are less critical early on than the MLP modules.
Interesting. And did BlockPruner's iterative process kind of naturally discover this? Like, did it tend to remove more MHAs?
It seems so. Its pruning pattern showed it tended to remove a greater proportion of MHA blocks compared to MLP blocks, especially to reach similar overall pruning levels. Now, why is that pattern removing more MHA blocks particularly important from a practical standpoint, beyond just reducing the model size?
Ah, right. This has a really crucial practical benefit related to inference speed.
Speed, okay.
Removing MHA blocks significantly reduces the usage of the key value cache, or KV cache.
Right, the KV cache is a big memory hog during generation.
Exactly. It's a major bottleneck, especially for long sequences, so reducing its size directly translates into faster inference times. And the paper's results showed BlockPruner achieving greater speedups compared to other pruning methods, partly because of this tendency to remove more MHA units.
So it's not just about making models smaller on disk, it's also about making them faster when they actually run. That's a double win.
Definitely. Another interesting finding from their experiments was about the data they used for the perplexity calculation. It mattered.
Oh, so?
Yes, they found that using an instruction-following dataset, like Alpaca, to calculate the block importance yielded better pruning results, better downstream task performance than using a general text corpus like Wikitext2.
Okay.
Which is a valuable insight, right? It suggests the calibration data you use to measure importance should ideally be relevant to the kinds of tasks the final pruned model is actually intended for.
Align the pruning data with the use case. Makes sense.
Yeah, and interestingly, they also did a study on sample size for that calibration data. They found that using more than about 256 samples didn't really lead to significant improvements in the pruning quality.
Oh, that's useful. So you don't need a massive data set for the calibration step.
Seems not, which is good for practicality.
And importantly, you mentioned it worked on newer models too. And what about reasoning? Sometimes pruning really hurts complex tasks.
Right, they showed the method generalizes well, not just to the older Llama 2 models, but also to newer architectures like Mistral and LMA3. And crucially, yes, it managed to preserve complex capabilities like reasoning. They tested on tasks like algebraic word problems and a few other diverse benchmarks, and BlockPruner maintained performance reasonably well even after significant pruning, which is often a big challenge for these compression techniques.
Okay, that's impressive. So bringing this all together, what does this mean for you, the listener? Maybe you're building with LLMs, or maybe you're just trying to keep up with the crazy pace of AI advancements.
Well, I think it means that researchers are digging deep into the actual architecture of these models, getting really clever and, academically grounded in finding ways to make them more practical. BlockPruner offers a path to significantly compress these models,
Making them smaller
making them potentially deployable on less expensive hardware or maybe reducing your cloud compute costs
and faster.
and faster, right, without completely crippling their core capabilities like language generation and even that complex reasoning we just talked about. It's a really concrete step towards making powerful LLMs more accessible, more democratized.
It really underscores that understanding the internal structure of these models at that fine-grained level is crucial for developing truly effective optimization techniques. Just treating them as monolithic black boxes or only pruning whole layers might be missing where the real inefficiency, the real redundancy, lies.
Exactly.
Targeting the right granularity for intervention seems to make a world of difference.
Precisely. It highlights the sort of non-uniform nature of redundancy. It's not just concentrated in whole layers, but distributed throughout the substructure within those MHA and MLP blocks.
The paper sounds pretty thorough, but do they mention any limitations or areas where more work could be done?
They do, yeah, they're quite upfront about it. They note that while perplexity worked well as an importance metric in their studies, it might not be the absolute optimal one. Exploring other global metrics could potentially yield even better results down the line.
Okay.
They also mention that while their iterative search is powerful, other, perhaps more sophisticated search algorithms might exist that could find an even better sequence of blocks to remove, maybe finding better trade-offs.
Makes sense. Always room for improvement.
And finally, just due to the sheer computational cost of training and evaluating these huge models, they weren't able to test BlockPruner on the absolute largest models out there, the real behemoths. Although they do state they believe the approach itself is scalable in principle.
Right, the compute barrier strikes again. Still, this has been a genuinely fascinating deep dive into the academic work behind making LLMs more efficient. We've seen how focusing on those fine-grained MHA and MLP structures
hmm
Using a global performance-aligned metric like perplexity
Right.
and employing that clever iterative search process can lead to really significant gains in model compression and performance retention compared to earlier methods.
It definitely shows that there's still a huge amount to understand about the internal architecture of LLMs and how to optimize them effectively by looking beyond just the surface level components. Lots more digging to do.
So here's a final thought for you, our listener, to ponder. If significant redundancy is found not just in layers, but deep within the MHA and MLP blocks themselves, what other specific fine-grained structures or even types of connections within these massive neural networks might hold surprising potential for future optimization? What else are we maybe missing by not looking closely enough inside the box?